but it's more so stuff that you have not really seen before ever. Still deals exclusively with right triangles, so that's always nice. But we're going to be kind of doing a bit more with that. Now, we're not actually getting into the trig side of things today. To start the trig stuff, we are first going to be going through just reviewing similar triangles, which we talked about way back in Unit 2B. All right, so go ahead and look at that first page of your big packet. So we're going to talk about similar right triangles. Now, again, we've already had like a whole unit on similar triangles, but this was probably like way back in the first term. So we examined extensively similar right triangles before. Now we're going to look specifically at just the right triangles that are similar. So similar triangles, we looked at triangles that were not necessarily right, just any triangle in its similarity. But now we're going to look at the right triangles. And the reason we are is because it has a very clear connection to trigonometry. Now, what makes right triangles similar and how to use similarity in these applied problems? So first off, let's talk about this. Let's kind of review for a bit. So think way back to Unit 2B. It was a while ago. Here, we have two triangles, ABC and DEF. How can we check for similarity? So how can we show that ABC and DEF are similar? So there were 4 postulates that we can test for similarity. Actually, I lied, there's 3. There's 3 postulates that we can use to test for similarity. Does anyone remember one of them? So it's like a combination of side and angle, or just angle or just side. So does anyone remember one of them? Side's one of them. Side angle sides, another one. There's one more. That's for congruency. Similarity is a little bit different. So remember, similarity means same shape, not necessarily the same size. So the other one is angle, angle, or angle, 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 meaning all 3 angles are congruent. Now, so remember, just to recall, in similar triangles, the angles are congruent. So in other words, the corresponding angles. So the corresponding angles are congruent, and the corresponding sides are proportional. Meaning, if we set it up as a fraction, you get the same number when you divide them. All right. So looking at this triangle, or these 2 triangles, which of these 3 postulates would be the easiest to check? Or the one to make the most sense to check, given the information that we have marked? Side, side, side. So we're going to use side, side, side. So now, what are my corresponding sides? So someone name me one set of corresponding sides between the 2 triangles. And remember, corresponding means that they're the same position. So it's the sides that are in the same position. So for example, what's the corresponding side to AC on the other triangle? DF. So those 2 are corresponding. What's the corresponding side to AB on the other triangle? DE. Which means that BC and EF are also corresponding. So what we're going to do is that we're going to take these proportions, and the way you set up the proportion is you do the new over the old. Or in reality, it doesn't really matter, but typically you want to do new over old. So, in other words, we want to show that DF over AC is equal to DE over AB is equal to EF over BC. So we want to show that all three of those proportions give us the exact same number when we simplify. So how will my proportion be set up for the yellow sides? So DF over AC. So what two numbers am I replacing with it? So it's the yellow sides. What are the numbers there, guys? 10 over 5. So DF is 10, AC is 5. We're going to do 10 over 5. And we're going to set it equal to, what about my green sides? So DE comes first, so it would be what over what? 8 over 4. And then my blue sides. 6 over 3. Good. So if you notice, all of our numerators come from this triangle. All of our denominators come from this triangle. You got to make sure when you're setting up those proportions, you keep that part consistent. So if you put the bigger triangle up top, that means you put it up top for all the proportions. If you put the smaller one in the bottom, you got to put the smaller one in the bottom for all the proportions. So what is 10 divided by 5? 2. What's 8 divided by 4? What's 6 divided by 3? So are all three sides proportional on the two triangles? Yes. So we can say that triangle ABC is similar to triangle DEF by side, side, side. Because all of the sides are proportional. They equal the same number when we set up the ratios. Now, using these same two triangles, since we know that they're similar, they gave us a bunch of different ratios that they want us to set up based off of the sides. So for each side, whatever side they have listed, that's what number we're going to put. So for BC over AB, what's that going to be with the numbers from those two triangles? So BC over AB. So what's BC equal to? Side BC, what's that equal to? 3. What's side AB equal to? So 3/4. BC over AC, what would that be? 3 over 5. Good. AB over AC over, good. EF over DE over, and that'll simplify down to not 3 over 2, 3 over 4. So we want those ratios in simplest form. All right. What about EF over DF? 6 over 10, and that simplifies down to 3/5. And then DE over EF. 8 over 10, that simplifies down to, what do you guys notice between, so these right here were from the first triangle. These right here are from the second triangle. What do you notice about those ratios? Aren't they the same for both? And if you notice, it's with the corresponding sides. BC is corresponding to EF. They're both the blue sides. AB is corresponding to DE. They're both the green sides, and so on and so forth. All right, so even though we're using ratios from different triangles, they still give us the same because we know they're similar. Does that make sense? Now, there's a whole reason that we're making these ratios. You'll see more when we do trig stuff tomorrow. Now, notice that not just the ratio of corresponding sides are equal for similar triangles, but also the ratio of relatively positioned sides that are equal. So the ones that we just did right here, part B, those are the relatively positioned sides. Meaning it's the ones that are close to each other. So AB. Miss Murphy. Yes. With your name is Kirsten's. All right, so relatively positioned, if you notice, it just means that they form angles. So like BC and AB, they're right here. Do you guys see how they form the 90-degree angle? BC and AC, that's the hypotenuse and one of the sides. They form an angle. And then AB and AC, so right here, don't they form an angle too? So that's what it means by relatively positioned sides. They form an angle of the triangle. So in the following diagram, DEF is a dilation of ABC. So DEF is a dilation of ABC by a scale factor of K. Because remember, that's what similar triangles essentially are. They're the same shape, meaning all the angles are congruent. But they're not necessarily the same size. Just put it on my desk, Caroline. And then you can throw your journal in the box that's like right next to my chair. So we're going to algebraically prove that these two are the same. That those two proportions are the same. So let's say that the lengths of AB and BC are X, Y, and Z. All right. Meaning that the scale factor of K, we don't know what that is. DE would be KX, KY, and KZ. Because remember, scale factors we just multiply to the sides, and that's what gives us our new sides. And K is just a constant. So K is a constant. So if we want to show that DE over EF is equal to AB over BC. All right, we're just going to take the values that we have. So we have DE and EF. All right, so I'm going to do DE, so K over X over K over Y, and that should be equal to AB over BC. So that would be X over Y. Now let me ask you guys this. What do you notice about the left side of the equation? What could happen? On the left side of the equation, what can you notice that we can simplify? The k's. The k's are the same number, so they go away. If you have k over k, that's 1. So we have xy is equal to xy. Is that a true statement? Are they equal? Yeah. So we just showed that DE over EF is equal to AB over BC. All right. Now, if we know that triangle MNP is similar to EFG, where MN is 10, NP is 6, and MP is 14, then which of the following is the ratio of EG to EF? So, let's figure this out. So we're going to draw our two triangles. And they're most likely right triangles. So let's say MNP, and then we have another triangle. We're going to call it EFG. Now, they just said they're similar. And they said that MN is 10, NP is 6 and MP is 14. And again, I didn't draw this to scale. So we know that they're similar. So let's go ahead and mark corresponding sides. What's the corresponding side to MN? EF. So MN and EF are corresponding. What's the corresponding side to NP? FG. Good. What's the corresponding side to MP? EG. So they want to know what's the ratio from EG to EF. So in other words, we want EG over EF. Now, the only way we can figure out this ratio, because they don't give us side lengths for EFG, but they do give us side lengths for its similar triangle. So what do you think I'm going to have to do? Use the what? Well, not necessarily the scale factor, but you're kind of on the right track. The core, we need to use the corresponding sides. All right. So what's the corresponding side to EG? MP. So we're going to put MP over, what's the corresponding side to EF? MN. So in other words, we're going to do 14 over 10 and simplify it. Because we know that those two ratios would be equal because they're similar, even though we don't know what the side lengths of EFG are. So what is 14 over 10 simplified down to? 7 over 5. So your answer is 1. Does that make sense to you guys? Using those corresponding sides? And again, the corresponding sides, you just got to look at how it's named. So MNEF, NP, FG, PM, GE. You just got to look at how it's named. All right, so now let's look at some word problems. So we can use these ratios, the relative sides of the ratio for corresponding sides of similar triangles to solve a variety of applied problems. So a person who is 68 inches tall casts a shadow that is 64 inches long. At the same moment, a tree casts a shadow that is 18 feet long. What is the height of the tree in feet? And we're going to round to the nearest foot. Now, I always tell my students, if they give you a geometry problem and there's no picture, you better draw it. So, we have some dude. All right, that dude is 68 inches tall. He casts a shadow. So this is the shadow. That's 54 inches long. Now I made that a really long shadow. Didn't really need to be that long. So he casts a shadow that's 54 inches long. All right, so the shadow's usually on the ground, so we're assuming that's a right triangle. Now at the same time, you have a tree. Not my best tree, but you get it. All right, that tree is, we don't know. All right, we want to know what the height of the tree is. Now, it casts a shadow that is 18 feet long. And again, we don't know what the height of the tree is. That's what we're trying to solve for. And it wants us the height of the tree in feet. So first off, what's kind of the issue that you notice before we even start the problem? What's kind of a glaring issue? Yes. Well, we don't know how tall the tree is, but that's what we were trying to find. But before we can even set up the problem, what's kind of a problem that we have? They're not the same measurements. One's inches, one's feet. So what do you think we're going to have to do? We got to convert the inches to feet. So that, or you can convert the feet to inches and then convert back. It doesn't matter. So, let's just convert inches to feet. How do I convert inches to feet? How many inches in a foot? 12. So there's 12 inches in 1 foot. So how do I convert from inches to feet? Yeah, so in other words, you divide by 12. All right, so we're going to divide 68 by 12 and 54 by 12, and they're not going to be pretty numbers. So in reality, I'm just going to leave them as fractions. All right, so if I put those in my calculator, so if I put those in my calculator, 68 divided by 12, not a nice fraction, but I want to leave it as a fraction, so I'm going to hit the math key and then enter twice. So 17 thirds. Because we want our answers to be as exact as possible when we round at the end. So this is equal to 17 thirds feet. We're going to do the same thing, 54 over 12. 54 divided by 12. Okay, 4.5. We can leave it like that. So this is 4.5 feet. So knowing that these two are going to be similar, because if you think about it, that tree and the person are, standing in the same spot at the same time of day, meaning the sun is hitting it at the same time. All right, how would I set this up? Using proportions. So we're going to be dividing. So in other words, it doesn't really matter which one you put on top, which one you put on bottom. So what do you want to put on top? The shadows or the objects? Okay, let's do the shadows. So I have 18 and 4.5, which means what would go on the bottom of those? The only other measurement we got, which is the objects, right? So what would go underneath the 18? X. Sit on my desk. What would go underneath the 4.5? 17 thirds. I'm going to put that in parentheses. Now, it's not too bad because what's all we got to do? I'll give you a hint. It's one of y'all's favorite things to do. Cross multiply. So I have 4.5x is equal to 18 times 17 over 3. Which, let me let you in on a little secret. If you want to do that in your calculator in one shot, you're just going to end up dividing by 4.5. So let's do that. So in my calculator, I'm going to do 18 times parentheses 17 divided by 3. Hit enter. I get 102. Then I'm going to divide it by 4.5. Now, it said to round to the nearest foot. So if I round that, about how many feet is that tree? So if I round to the nearest foot, not 3, to the nearest foot. So it's already in feet, so we just got to round that 22.666. 23. So x is approximately 23 feet. That's how tall the tree is. Does everyone understand how I did that? Yes, no, maybe. So again, be careful because especially like when you take Math 3 and you do the EOC, they love throwing in problems where the units don't match. The units of measure don't match. So if they don't match, you need to convert one of them, preferably to what they wanted. So they wanted it in feet, so we converted to feet. All right, let's try another one. A rectangular picture has a width of 4.5 inches and a height of 3 inches. If the picture is to be scaled such that the width is 6 inches, what is the new height? And then what is the length diagonal to the nearest tenth of an inch? So let's say we have our first picture. The width is 4.5 inches. The height is 3 inches. They then make a bigger frame, or they scale that picture to be bigger, where the width is now 6 inches, and we don't know what the height is. So, using what we know about similarity, let's set the proportion to solve for it. So what will my first proportion look like? So my first proportion is typically the one without the x in it. So what would that first proportion look like? What would my first proportion look like? You want two corresponding sides. That, or you want, no, I lied. So you want the one that doesn't have the x in it. You're going to set that up as a proportion. So using the picture that does not contain the x, not over 6. Using the picture that does not contain the x, so it's 4.5 over what? 3. Now we're going to set equal to, this is where you got to pay attention to the corresponding sides. What's going to go on top for the other picture? 6, because that corresponds to the 4.5 over what? X. Then we're going to cross multiply to solve. So I have 4.5x is equal to 6 times 3. So I have 4.5x equal to what? 18. What's the only thing I got to do to solve for x? Divide by 4.5. So x is equal to what? 4. So x is equal to 4 inches. Now, it also asks what's the length of that diagonal to the nearest tenth of that same picture. So the diagonal is if we draw from one corner to its diagonal corner, right here. So let's call this y. Now, here's my question. We don't have to use similarity for this. What can we use, though? So this is a picture. It's a rectangle. That means this is a right angle. What type of triangle is this? It's a right triangle. So we have 2 out of 3 sides of that right triangle, meaning what special formula can we use to solve for that third side? Good. A squared plus b squared equals c squared. What's that called? The Pythagorean theorem. So what would my c squared be? C squared is always your hypotenuse. So which side is the hypotenuse? Y is. So this would be 4 squared plus 6 squared is equal to y squared. What's 4 squared? Plus what's y squared? It's equal to y squared. So this would be 52 is equal to y squared. So y is equal to the square root of 52, which, put that in your calculator, round to the nearest tenth. Y is approximately what? So round to 1 decimal place. 7.2 inches. Good. So that's the diagonal. So this would be about 7.2 inches. Don't forget about the Pythagorean theorem. I can guarantee you this unit, you will be using it a little bit. At least kind of like the Pythagorean theorem is like if they ask you to find a side and then after that they ask you to find another side. So just keep a squared plus b squared equals c squared kind of in the back of your brain. All right, last one for this section. So one of the classic engineering uses of similarities, this is actually a real world scenario, is measuring the width of a river, which is not easy to do with a tape measure, obviously. If y'all have seen like the Neuse River or the White Oak River, which are the closest ones around here, you know, they're pretty wide because we live right by the basins of them. All right, so engineers spot 2 points on opposite sides of the river, A and B. They measure the distance of BD along the river and then the length of DE perpendicular to the river. So in other words, spots on the ground. Finally, they draw a line AE to mark the intersection of AE and BD at point C. So explain why it must be similar to, so explain why this triangle needs to be similar to this triangle. So let's think about it. Why must they be similar? Well, let's talk about it. So we know they're right triangles. So isn't that already one angle that's congruent? So are the right angles congruent? Yes, no, maybe? Yes. What's another pair of angles based off of this picture that we know for a fact are congruent? So those aren't angles, those are sides. Remember, angles we say with 3 letters where the vertex is in the center. Good. So CB and ECD are also congruent. Why? What are those angles? What's that called? Starts with a V. Vertical angles. So those 2 angles are vertical. So if we have 2 congruent angles, what postulate of similarity lets us show that those are congruent? Or not congruent, similar. What similar postulate that we talked about on the previous page lets us say that those 2 triangles are similar? Think about it. We only got 2 angles marked. So it has to be angle, angle. So because angle ABC is congruent to angle EDF, or EDC, sorry, and angle ACB is congruent to angle ECD, then triangle ABC is similar to triangle EDC by angle, angle. So that's why it's similar. We had 2 angles that we knew for a fact were congruent because of geometric properties. Because obviously 90-degree angles are always going to be congruent to each other. And we had a set of vertical angles. So now let's do some side assumptions. So BD, so the length of BD, so this entire length right here is 225. CD, so this little length right here is 30. And DE, so this little length right here is 12. And it wants to know what is the length of the river. So what we're trying to find is AB. So we'll call that X. Because that's the length of the river. Or the width of the river, whatever. So from bank to bank of a river. That's typically the width. So let's kind of make us a plan. So first off, corresponding sides. What's definitely a set of corresponding sides that we know of? Between the two triangles, what's definitely a set of corresponding sides? Now keep in mind the orientation did flip. So look in terms of where the right angle is. What is a set of corresponding sides? A, B, and D, E. So A, B, and D, E are corresponding. So these two are corresponding. What's another set? Look at what they gave us. Specifically, what do we want to use? So they gave us DC. So what's the other set of corresponding side that we should probably use? BC. So in other words, our proportion is going to look like BC is equal to AB, and that should be equal to DC over ED. So that's how we're going to set up our proportion. But I don't know what the length of BC is yet because they told us the length of BD, not BC. But how can I find BC? $225 what? Good. We already have a piece of BD, which is 30, and then we have the whole. So all we got to do is just subtract the two. So I just got to do 225 minus 30, which is what? 190. You sure? Put in your it is 195 if you put in your calculator? Okay. So this would be 195. So that's what's equal to BC. Now we can set up our proportion because I got everything. So I have 195 over x is equal to 30 over 12. So let's do some cross multiplying. So I have 30x is equal to 195 times 12. What's 195 times 12? 2,304? That's what you said? Okay. That the right number? Okay. 4D, okay. And then we're going to divide both sides by 30. So what's x equal to? $78. 78 what? Feet. Make sure you put the units as well. So the length of the river is 78 feet. That's how long that riverbank is. Any questions on how you use similar triangles to solve for sides? It's not too bad. You really just need to pay attention to the corresponding sides. All right. So that's it for similarity. Now, we're going to switch gears right now, and I want you to go to that other packet that I gave you with special right triangles. So just look at the first page. So something else that I want to talk about, besides similar triangles, something else that we need to talk about is something called special right triangles. These are very, very special cases of special right triangles. All right. And what it means is that essentially these two types of triangles, first off, they're right triangles, but they have very specific angle measures. And those angle measures dictate kind of how you can find the sides without using Pythagorean theorem or trig. All right. So the first one we're going to talk about is 45, 45, 90, meaning it has two 45-degree angles and a 90-degree angle. So we're going to do this together for both of these. So for all three of these triangles, we're going to calculate the hypotenuse. So these hypotenuse. What can I use to calculate the hypotenuse? What theorem do we already talk about? Pythagorean theorem. So a squared plus b squared is equal to c squared. Now, notice how both of these sides are congruent. And that's true because they're both across from the same measure of angle. If sides diagonal to two of the same, sides that are opposite of congruent angles in a triangle are always congruent. That's just a known fact. So how would I set up the Pythagorean theorem for this first one? Three squared plus 3 squared is equal to, let's just leave it c squared. What's 3 squared? Plus 9 is equal to c squared. So that's 18 is equal to c squared. So I have the square root of 18. Now, I want this in exact form because it says to leave our answer as a square root. So I just don't want to do square root of 18 because we know how to simplify radicals. So how do I simplify the square root of 18? What's the highest perfect square factor in the square root of 18? Highest square, perfect square, 9. So this is the square root of 9 times the square root of what? What times 9 is 18? 2. So c is equal to 3 square root 2. So this side is 3 square root 2. Let's do the other two. How do I set up the next one? Five squared plus 5 squared is equal to c squared. What's 5 squared? 25. So 25 plus 25 is equal to c squared. So 50 is equal to c squared. So c is equal to the square root of 50. I want to simplify 50. So what's the highest perfect square that goes into 50? 25. And 25 times what is 50? 2. So this would be the square root of 25 times the square root of 2. So that would be equal to what? 5 square root 2. So this side is 5 square root 2. All right. Last one. How do I set it up? 8 squared plus 8 squared is equal to c squared. So what's 8 squared? 64 plus 64 is equal to c squared. So that's 128 is equal to c squared. All right. Take the square root of both sides, square root of 128. Well, what's the highest perfect square that goes into 128? I'll give you a hint. It's a number that we've already used in this problem. 64. 64 times 2. So this would be square root of 64 times square root of 2. So what's c equal to? 8 square root 2. So these are all the same. So these two sides were congruent, and these two sides were congruent. All right. I'll just put on my desk. Now, the next thing we're going to do is calculate the ratio of the two legs. So, the two legs. Who remembers what the legs of a right triangle are? It's basically the sides that are not the what? The hypotenuse. So the two legs are going to be the two sides that we use in the Pythagorean theorem to calculate the hypotenuse. So what's the ratio of the first triangle of the legs? How do I set it up? What over what? 3 over 3, which is equal to what? 1. What's the second one? 5 over 5, which is equal to what? 1. What's the last one? 8 over 8, which is equal to what? 1. So in other words, the ratio for all three of them is 1. And it's because the two sides are congruent. Which, if you divide the same number by itself, you always get 1, regardless of what number that is. Now, let's calculate the hypotenuse to the leg. So we're going to do hypotenuse over leg. So for the first triangle, what's the length of the hypotenuse? 3 squared root 2 over what? 3. So if I simplify that, what happens? What goes away? The 3's go away. What am I left with? Square root of 2. What about for the second one? How would I set it up? Good. 5 square root 2 over 5. What goes away? 5's are gone. Left with a square root of 2. What about the last one? 8 square root 2 over 8. What happens? 8 goes away. We got the square root of 2. All right. So if you notice, we get square root of 2 for all of them. So we get square root of 2 for all of those ratios. So here's my question. Look at the numbers that we got for these two triangles. How do you think I can get from the leg to the hypotenuse without having to do Pythagorean theorem if I knew it was an isosceles right triangle, meaning the two angles were 45 and both sides were congruent, both legs were congruent? What's kind of the most straightforward way? So how would I get from 3 to 3 square root 2? How would I get from 5 to 5 square root 2? How would I get from 8 to 8 square root 2? How would I do that? No. Couldn't I just multiply by some number? What number would that be? Not 2, but you're close. What symbol's over the 2? Square root of 2. So to get from the leg to the hypotenuse, we would multiply the leg times the square root of 2. Now, that means that to get from hypotenuse to leg, if we go backwards, what do you think we're going to do? What's the opposite of multiplication? Division. So we would divide by the square root of 2. So we take the hypotenuse and divide it by the square root of 2. All right. Another way you can think about it is that if you rationalize this, if you rationalize this denominator, you would take the hypotenuse and multiply it by the square root of 2 over 2. That's the other way you can think about it. That's just if you rationalize the denominator. So let's look at these. So now we're going to find the legs. So we got the hypotenuses. So how can I find these two legs? And remember, these two legs are going to be congruent. So all these legs are congruent. Not to each other, but they're congruent to, like within the same triangle, they're congruent. So I got the hypotenuse. How do I go from hypotenuse to leg? I just do what? What did I just say up here? We divide by the square root of 2. So 7 square root of 2 over the square root of 2. What's that equal to? 7. Square root of 2's cancel out. So both of these legs are 7. What about 18 square root 2 over the square root of 2? That's just 18. So these two legs are both 18. Now this last one, we know we got to divide 10 by the square root of 2. But remember, we don't like radicals in the denominator. So what do we actually have to do with that? How do I get rid of the radical out of the denominator? Right. We have to rationalize, so we multiply the top and the bottom by the square root of 2. So if I multiply dead across, this will be 10 square root of 2 over the square root of 2 times 2, which is 4. What's the square root of 4? 2. So this is equal to 10 square root 2 over 2. Is that fully simplified? Nope. What's 10 divided by 2? 5. So this is 5 square root 2. So this one's 5 square root 2. This is 5 square root 2. So this is always true with 45, 45, 90 triangles. So the takeaway from this is if you have a 45, 45, 90 triangle, it's meaning you have a right angle and two 45-degree angles. And those angles will be congruent. All right. Here's the hypotenuse. Here's the two legs. And remember, those two legs are also congruent. If your legs are equal to A and A, so they're the same length, the hypotenuse will be equal to A square root 2. So in other words, if you go from leg to hypotenuse, you would take the leg and multiply it by the square root of 2. If you're going from hypotenuse to leg, you would take the hypotenuse and divide it by the square root of 2. And then make sure you rationalize denominator if needed. So in other words, if the square root of 2 doesn't cancel out on the bottom like it did for the first two problems, you have to rationalize. And again, this only works if you have this angle configuration of the triangles. So two 45-degree angles and a 90-degree angle. That's the only time this configuration works. Does that make sense? All right, so let's try some more problems. So I always tell students to kind of mark what they're given. So for letter A, the 6, is that going to be a leg or the hypotenuse? Leg. Now, since this angle's 45, that means this one's automatically 45 because if you subtract 90 and 45 from 180, you will get 45. So that means this one's also the leg and this is the hypotenuse. So automatically, what's the length of this leg right here? 6. What's the length of the hypotenuse? 6 square root 2. Just multiply 6 times the square root of 2. All right, what about here? So 11 square root 2, is that the hypotenuse or the leg? It's the hypotenuse because it's across from the 90. That's how you know. So these two are the legs. So how do I get from hypotenuse to leg? Divide by the square root of 2. So what happens to the square root of 2's? They go bye-bye. I'm left with what? 11 for both. Now for number 2, if the hypotenuse of an isosceles right triangle, remember isosceles right triangle means both sides are congruent, meaning it's automatically 45, 45, 90. That's the only way a right triangle can be isosceles at the same time. Is 20. What is the lengths of the legs? So let's draw the picture. So I have a right triangle. I know it's 45, 45, 90. meaning these two legs are congruent because it's isosceles, and my hypotenuse is 20. Ralph, just put your test on my desk. Don't worry about it. I'll grade by hand. So, how do I find the two legs? What do I do? If this is the hypotenuse. 20 over the square root of 2. What's the issue? Square root of 2 is in the denominator, and they can't cancel out. So how do I get rid of it? Good. No, I'll grade by hand. So I have, if I multiply it across, I have 20 square root of 2 over the square root, just said square root of 2 times 2, which is 4. So this is 20 square root of 2 over what? 2. So this will be what? 10 square root 2. Good. So both of these would be 10 square root 2. All right. Now, let's simplify these radicals. So what's the largest perfect square that goes into 32? 16. 16 times what is 32? 2. So I have square root of 16 times square root of 2. So what's the answer? 4 square root of 2. Guys, we're on the short packet that says mathematic on the second page. All right. What's the perfect square in 20? 4 and 5. This would be square root of 4 times the square root of 5, so 2 square root of 5. Now this one, I just have to rationalize the denominator. So I have to multiply the top and the bottom by the square root of 2. So this would be 40 square root of 2 over the square root of what? 4. So that's 40 square root of 2 over 2. So that'll be what? 20 square root of 2. All right, last one. So, got that special right. It's a 45, 45, 90. And they gave us which side? Is it the leg or hypotenuse? It's a leg. So this is a leg as well. This is hypotenuse because it's across from the 90. So to find the missing sides, what's the easiest side to find first? The other leg, which is what? Good. 6 square root of 2. All right. How do I find the hypotenuse? So if I go from leg to hypotenuse, what do I do? You multiply by the square root of 2. So I'm going to do 6 square root of 2 times the square root of 2. So again, we multiply outside by outside, inside by inside. We talked about this in the last unit. So this will be 6 square root what? 4. What's the square root of 4? So I got 6 times 2, which is 12. So the hypotenuse is 12. Any questions on how you find the sides of special right triangles, at least for 45, 45, 90? Now, the other type is a 30, 60, 90. We will talk about that tomorrow. All right, because we have to break out protractors and everything for that, and I don't feel like doing that right now. Okay, so that's it for the lesson today. So your homework is a delta math. Now, I will say that this delta math, there are going to be a little bit of pieces that you can't do quite yet. Let me just show you which one it is. And by the way, this delta math is going on this term, this new term that we're in, not the one that just ended. So you should be able to do everything except for these last 2 sections. Don't do these last 2 sections yet. All right. So you can do the first 3 sections, just don't do the last 2 sections yet. Yeah, those are 45. Good. So you got about 20 minutes. You should be able to go ahead and start working on that. So again, you can do the first 3. Don't do the last 2 just yet. We got to talk about